Okay, well, thank you. It's a pleasure to be here to speak with students at the University of Tokyo. And I'm going to really talk about taking a scientific approach based on research on how you can maximize learning. And particularly the things I study is how you can learn to think like an expert scientist or engineer, and how you can learn to do that as quickly and efficiently as possible. Now, I actually got started in this work about 25 years ago when I was working with graduate students in my atomic physics research lab, the one that made Bose-Einstein condensation. And what I got curious about was a basic sort of scientific puzzle, which, or I found it a scientific puzzle, which I had all these students come in as new physics graduate students to work with me, and they'd had many years of great success in their coursework. They scored high on all these tests, but I found they really couldn't do physics very well at all when they started. And after a few years working in the research lab, then they had become expert physicists. And so I got started wondering about this kind of puzzle of why learning to do so well in courses didn't make them already physicists. And so, okay, some things, there we go. So I really started thinking about this like it would a science or physics question, and I went out and I looked at what the research said about how people learned, and particularly about how they learn physics, to try and make sense of this basic puzzle. And what I realized was that it was possible to approach the teaching and learning of science just the same way that I approached actually doing physics. That you can actually do controlled experiments, and you could compare different ways of teaching, and you could measure the results in terms of what students were actually learning, and you could get data. And so it meant that you didn't have to think about teaching anymore as just something that people just went in and tried, and you sort of saw if students liked it or not. You could really measure results, have principles and methods, just like you could in science itself. And this way of approaching the learning and teaching of science was something that actually had started before me. It was about 30 to 40 years ago. It had started in physics at universities, and it's now spread across all the sciences and much of engineering, particularly in North America, as sort of studying how people are learning these subjects. And so I've been actually doing research for several decades in this. And, so I had one research group looking at atomic physics and another research group looking at how people learn physics and better ways to teach physics. And one thing I've been doing, particularly in recent years, is bringing in cognitive psychology, the research on very basic ideas about how the human brain thinks and learns, and then see how we can take that and apply it in the classroom, the universities, to help students learn better. And so in this process, I've learned a great deal about learning and teaching science, and some of what I learned is very different from what students are often told they should be doing by their professors. And so I'm going to give you an example here of an experiment that's been done. And for this, you're going to actually have to make predictions. Think about what the choice is here, and I'm going to call on you to make predictions about which you think is the correct result. So in this experiment, they took 3 groups of students that they selected to be very equivalent. And one group of students, they had, so in the first choice here, the first group of students, they came to class, they listened to the lecture, and they took notes on it, very much like most students do in class. The second group of students, they had go to the lecture, but instead of taking any notes, they were told to just focus on not taking notes, just trying to learn as much as you can from the lecture. And the third group of students, they gave them the lecturer's notes that the lecturer had written out and said, go home and just spend, well, I actually had them in a next room, just study these notes and try and learn as much as you can from them. And then after that, they gave all 3 groups the same test on covering the material to see which of these 3 groups learned the most. And so the choices that you're going to have to choose from to predict was which of these groups learned, the order of how much the different groups learned. And so your choice, and I'll have you raise your hand as to which choice you have, but the first group would mean that the group 1 learned the most, group 3 learned the least, and then, for example, in this one, it means group 3 learned the most, and group 2 learned the least. Okay, and so now...
Sorry, I have a question.
Yeah.
Some students didn't go to lecture.
So this was a very controlled experiment, so this was looking at just each of the students. You know, it was more controlled than most random students. So they knew that each of these students did each of these things, okay, that they're measuring, okay? So raise your hand if you think that the A is the result of the experiment. Okay. What about if you think B? So, what about C? D? And what about E? Okay, this is a very interesting group. You're almost evenly split. Just about the same number of people has predicted each one of these. So, what's the correct answer? Well, the correct answer is B, that the ones who did not come to lecture at all learned the most. They were studying the lecture's notes. And the ones who came to class took notes, doing the same thing that most students do, most students are told to do. They're the ones that learned the least, okay? So why should this be the case? So what I'm going to do is give you a chance to talk to your neighbors for just a minute about trying to come up with reasons that you think can explain this. And then I'm going to see if I can get a few volunteers from the audience to offer your reasons of why you think this kind of result would make sense. So you now get to talk to each other to try and figure out this strange result. All right. So there was obviously lots of good discussion. If this was a real class, I would have loved to have been walking down among you, listening in on these conversations to understand how you're thinking about it. But today, we're not going to be able to do that, but I will be able to. Can I get just a couple of you to offer to volunteer reasons you think why it could have come out this way? And I think we need to have microphones, so if you have an idea, raise your hand and they'll give you a microphone so it can be recorded. So, anyone want to be brave and try an explanation? Okay, yeah, there's...
Well, I thought the third group did better because if you go to the lecture and just take notes, you feel like you're studying, but maybe they're not like learning. But if you just get good notes and study by yourself, you know what you're doing and you have responsibility, and that's why they did better on the test.
Okay. Other ideas?
So I chose the B because if students go to the lecture and taking notes, they should pay their attention to taking notes, but not they can't focus on learning, so it can decrease the effect of learning, I think.
Okay, good. Any other last people anxious to make a comment here? Oh, okay, so we'll go on. So basically, the answers that you were given were in fact essentially the right reasons on this. And it's interesting that when I pose this question to students, so one thing that's a little different is that usually I get most students are following what the official instructor message is, that you should come to class and take notes will be best. But then when I give them a chance to talk to each other, they always come up with the right reasons, just like you did. And so if you look at this, if you compare going to class and taking notes versus not taking notes, but remember I said they were paying attention during class. They were doing their best to learn it, but just not taking notes. Well, the difference there is the taking notes takes added attention. So you're having to split your attention between listening to what that lecturer is saying, and they're talking really fast and covering lots of stuff, and then also trying to pay attention to summarizing it and capturing it as best you can and taking notes. That split attention, that sort of split capacity of your brain reduces the amount of focus you can give to really thinking about the ideas and learning from it, as both of the people talked here. And so that's really why, too, not taking notes and paying more attention to listening actually helps the learners in that case. Now, if you look at the comparison between coming to class and then paying it full attention versus the ones who just stay home and review the lecture's notes, then it's just, again, as the two students here said, but I'll go into a little more detail on this. The benefits of just studying the lecture's notes is because the learner can do it at their own speed. They can really think about the materials there, and they can take time to process and make sense and learn from it without having to worry about the fact that the lecturer keeps talking and talking and goes on beyond where they can keep up with. And so, and also we see that in these studies, when you're hearing something for the first time about some new material, it's really hard to organize it in your own mind and understand the different pieces and how they connect together. Whereas if you have it all laid out nicely in a good set of notes, that organization is much easier to follow than if someone's just telling you. And so because of those reasons, that's really why 3 ends up better than 2. And so that's why the experiment comes out this way. And so these ideas are, just very fundamental ideas about learning and the importance of focused attention and processing being necessary to actually learn, particularly learning complex things like thinking like scientists and engineers. And so this experiment and this explanation is really, you'll see all the stuff I'm going to talk about is going back and just going into more details about these basic ideas of what maximizes learning. So before I get into that, though, I'm going to quickly go through another experiment that was, now this is done in a real classroom with real students, and so dependent on whether they came to class or not, et cetera. But this was one which I was involved with, and we took a big introductory physics course, the first term of physics. I'm sure it covers the same topics as, or second term of physics in this case, same topics as covered it here. And there were two, it was such a big course, there were 3 sections, and we picked 2 of these where the student populations looked very, very similar. We had a lot of test data on both of them. It was just the same. And then in the 2 sections, they covered exactly the same set of material, the same learning objectives, covered in just 1 week of lectures on the topic, and then gave the students a surprise test right at the start of the following class. And so the students weren't really doing any studying of this material outside of class, and so this was really measuring just what they learned from sitting in class and hearing about the material. And the comparison was a class which was taught in the standard lecture style that I'm sure most of you are familiar with, of someone standing up there talking while the students are listening to them, but by someone who taught this material a lot of times and had good student ratings as a teacher. And then the other section was taught by someone who hadn't taught very much, but they were a new PhD in physics, but they'd been trained in these methods and principles of scientific teaching that I'm telling about today. And so in that experimental class, the students had this short reading they had to do before coming to class, and they had a brief online quiz to check that they'd done it. And then during class, rather than just sit there and listen, they had questions to solve, and they had to use little electronic response systems that they had to, submit answers with, or they were working in worksheets where they wrote down solutions on how things worked out. And during that time, they would be regularly doing what I had you do earlier of talking to their neighbors to try and make sense of things. And so this is an example of a kind of question that they would be given, that they would have to each use their electronic response system to answer to, which is if you have the battery, a circuit with this battery and light bulbs there, and you close that switch, what's going to happen to the brightness of bulb 2? And they have to think of answers and the reasons for it, and they talk to each other as they try and make sense of this. And there's actually quite a lot of discussion, talking by the instructor, but it's not sitting initially just telling students things preceding when they tried to figure out. It would be the follow-up to this question, that the students would try and answer this, and they'd talk about it. The instructor would see their response and listen to the kind of discussions they would have, and then would follow up their discussion, explaining what the correct answer was and why, and even more importantly, get out the incorrect reasoning that students had learned, and then help them understand why it was incorrect and how they could do the better on that. And so then this kind of teaching also then generates many follow-up questions from students. Okay, so this is just a review of this. I'm not going to have you make predictions on this because you'll all figure it out. You were good enough on the first one that you won't have much trouble on this question. So here's what the actual results were. So this is a histogram with the number of students this way versus their score on this test here, and the distribution, great. Yes. So here's the number of students, their score on this test, and you can see how the learning from the traditional instructor here, the distribution is much lower than the one with this scientific teaching. The one subtlety here is that this was a multiple choice test, carefully developed multiple choice test. And so if a student just randomly guessed, they could, on average, they'd score 3. So the amount of learning is really how far they got above 3. And so you can see there's an enormous difference between these two distributions, that the students, that had this sort of scientific teaching method learned enormously more. And this was true for both the top students in the class and the bottom students. Like I say, this entire distribution moved up. So it's just much better learning for everyone. So what's behind these kind of results? They're not sort of mysterious. If you look at the basic principles of what we know about learning from cognitive psychology, you see that this is exactly what you expect, and this can be used as your learning. This is really the guidance you should follow as you try and make sure you're learning more. And it's really that the effective learning of any sort of complex subject like science and engineering, it really requires practice at the specific thinking and the decision-making process that you want to learn. You have to practice that, and then you have to get feedback on your practice, on how you're thinking and how to improve it. And so it's really very much like learning any sort of athletic activity, right? You go and practice it, and you get feedback from a good coach on how to get better. And it turns out it's just the same in learning. And so from your perspective, what you want to do is you want to be looking at the learning of this as thinking about, okay, whatever subject it is you're supposed to be learning, try and break this down into practice, practicing certain thinking tasks and figuring things out, not just kind of reading over material and reviewing it, but testing yourself on it in the same way that if you want to learn to hit a golf ball better, you would practice doing it and see how well you could do and then what you might do to get better at it. So the next question, though, is exactly what sorts of things should you be practicing, okay? And this is where you can get a lot of help from the research on expertise, research on how experts think. And it turns out this has been studied quite a lot across many different fields of endeavor, whether it's chess players, historians, scientists, etc. And they find that there's certain very basic elements that make up expert thinking in all of these different areas. So one of them that every one of you could guess is that experts have a lot of knowledge about their particular subject. But what's more important than just the knowledge is the way that knowledge is organized. And so in every field of science, engineering, and many other history and so on, in each field, there's a very specific way that experts have organized all their knowledge. And this organizational structure that they have allows them to be very efficient and effective at retrieving the particular information that's useful in solving any particular problem. And so what we talk about as scientific concepts, for example, is just the way that scientists in a field have taken a whole bunch of different pieces of information, different experimental results, and seen how they can organize them in sort of one big chunk And so when they are faced with some new problem, then they can be very efficient at deciding, oh, all of that information, no, that's not really relevant to this problem. Oh, but all of this part of information, this concept is, and so I can use it to solve it. The third aspect of expert thinking is an ability of experts to monitor their own thinking when they're working on problems. So they're able to ask, themselves, do I really understand this? Is this a sensible way to be solving this problem? And they can actually have ways to answer those and then change what they're doing accordingly. And this is one thing the research shows big differences between what we call, expert problem solvers and novice problem solvers. Novice problem solvers will sort of start working on one approach, and they'll just keep working and working and working on it, even though it may not be very productive and not get anywhere. The expert problem solvers will work on it for a little while, and then they'll realize, no, this isn't getting me in the right direction. I need to step back and find a better direction to go. And so this is the kind of thing you can be practicing yourself doing as you're working on things, is periodically stopping and saying, is this really taking me in the right direction, or should I try something different? Okay, so the research on expert thinking, what it's shown is that these basic elements of expert thinking, no one has those automatically. They really come only from this intense practice, and it takes actually many hours of intense practice to develop this capability of thinking and to reach a sort of very high level, professor, at Tokyo University level of expertise. It's actually many thousands of hours of practice. And what we're now realizing is this is basically a biological requirement, that in what happens is you do these many hours of intense practice, you fundamentally change the brain. And the brain is working very hard to make sense of this, to figure things out. And it's actually rewiring itself. The neurons are being connected in different ways as a result. And it just takes these many, many hours to get enough changes in the brain for it to be more expert-like. And it's really within this rewired brain that expertise lies. And so your job as a learner is just to think about how you can rewire your brain as efficiently and effectively as possible to develop those capabilities. And it means you just have to be thinking about exercising your brain in the right way. And so this process involves the same sorts of things I talked about before, of finding challenging but not impossible tasks and questions, covering the material, but really practicing the expert thinking decisions that you want to learn. And so to get a little more specific about what some of these ideas would be, I want to give you some general components that apply to every field of science and engineering. For example, in every field, there's a set of concepts or mental models that experts regularly use in that field. But more importantly, there's very specific criteria they have for when they have a problem they're working on, being able to look at a specific concept and decide whether that's useful in that problem or not. And so this idea of going through when you have a problem and very carefully deciding which of these concepts and how I test which of these concepts apply and are going to be useful there, that's practicing the kind of expert thinking you need to learn. There's practicing looking at a general problem and deciding what information here is relevant for solving that problem and what's just irrelevant and I can ignore in this case. Once you get an answer, think about ways, and each discipline has these, of testing if that answer makes sense, okay? Or it's, you know, if it doesn't make sense, then you should go back and figure out something better. And then finally, every field of science and engineering has specialized ways of representing information, whether, you know, it's through equations or special kinds of graphs or whatever. And experts then can move very smoothly between these different representations of the information, and in that process get new insights about understanding and solving problems. So these, now, you know, so I said, well, these are the kinds of expert thinking you need to be practicing. But notice I didn't list any particular topics or subjects here, whereas, you know, all your education, they say, well, you have to go study all these list of topics. And the important aspect of here, and this is something the research has made very clear, is that all of those particular, that knowledge, those topics, they are important, but they're really only important and useful if you learn them in this part of this framework of expert thinking involving all of these kinds of things. Those are what tells you, or how to know when and where to use that knowledge and actually then be more expert-like in your thinking. So I'm just getting close to the end, then we'll have time for questions. But some of the things you can very specifically do to improve your learning, okay? So the first one is really quite important, but often not recognized enough, particularly in modern days when we have, you know, all the cell phones and computers and all these different sources of information. You really, for studying and learning to be useful, you really have to be focusing all your attention on it. If you split your attention between, you know, you're supposed to be studying a textbook, but you also have the television going and you're checking email and, you know, text messaging friends all the time. It turns out we study these things, people think they're learning something, but they aren't. They just, you know, this split attention is really completely completely ruins all your learning. You can think about this idea of making enough focus to strengthen particular neuron connections. It means your brain has to be totally focused on that task. And so it's just the same as, you know, if I want to build up a muscle here, I really have to use that muscle as strenuously as I can. If I just spend a little time lifting my arm up and down, it's no strain to the muscle and doesn't get any better, and your brain is just the same way. So basically, you know, either completely focused studying or don't bother. The second thing that's important is keep checking your own thinking. Periodically stop and seeing what the other ideas you can bring in, things you know, other processes, other people, to continually check if you're thinking about something, your problem solving is making sense or could be better. This one is also very important, and I stress, when you get something wrong, whether it's, you know, on an exam or just in working something out, what's important is not to know whether it's wrong or not. It's to really understand what about your thinking is wrong, and so what you can change so you can then do something different when you see a problem like this, and you can put that practice of taking a different approach to the problem right away to sort of then practice at doing it right. And so anytime you get something wrong, it don't stop when you just find out if it's wrong. You have to go and understand why you were wrong. What aspect of your thinking was you know, not going in the right direction, and fix that. It's really helpful connecting with all these things is when you do a problem, thinking about, okay, are there other ways to do this problem? Are there other approximations I could make or other ways I could approach this? Doing this kind of looking at things in multiple ways, this again really helps you developing to be a more expert thinker in these fields. And I talked a lot about how the importance of organizing all your knowledge in a subject, and this is something where, again, it's important for you to actually practice that. So as you get new topics and so on that you learn, new courses, spend time thinking about, okay, all the other things you know and how these things are related, how they're different, and really building up that knowledge organization framework that you have. And then finally, one that seems strange to be on this list, but it's actually really quite important, is you need to sleep. It turns out that if you study as people study learning, the brain, it sort of does a bunch of processing, all the sorts of things I talked about, but that doesn't really go into storage, if you like, until after you sleep. We talk about that consolidating learning, okay? So that means if you decide, okay, you know, I can put in an extra 2 hours studying or 3 hours studying, and so I'll only sleep 2 or 3 hours tonight, that's never going to benefit you, okay? In the long run, that sleeping actually really directly contributes to learning, and we can measure that people, I mean, it seems strange, but you can, for certain tasks, you can measure how much people know after they've studied it, and then you can test them on it the next day after they've slept, and they actually do better after sleeping. So, plus, of course, it stays around longer. Okay, so I'm just going to finish up with just giving you one example of how these kinds of different ways of teaching, where students are really doing much more of this thinking and processing actually during class time with a professor, of how this is happening at other places. And Stanford, where I am now, partly because of my work and partly some other faculty, just over the last 2 years, year and a half, it's actually the majority of courses taken by students who getting degrees in physics. They're more advanced courses here, 2nd through 4th year. These have all been getting, most of these have been getting transformed into this different way of teaching. And so classrooms, instead of looking like this now, are looking like this, with students working together, solving problems, and the instructors are circulating around here, acting like sort of coaches during that process. And so, you know, they're using these methods of effective teaching, which really just mean they're getting the students to do the things that count as effective learning. They're doing some preparation, usually reading before class, and then there's not a lot of just telling the students things ahead of time. The students are working on things, you know, in something like advanced physics. Most of this is worksheets, because you've got to have calculations and mathematical manipulations like you can see students doing there. And then the instructor is acting, giving feedback on the students' work, helping them out as they go around along. And some of the obvious things we're seeing in this is, one thing that's very interesting is that the attendance in the classes has gone up dramatically. And so it's very close now to 100%. It's basically every student who's not seriously ill now always comes to class. And I think this is largely because they find the classroom, they're learning so much more, it's more valuable, they don't want to miss that opportunity. The instructors, professors are finding they're covering actually as much or more material, even though the students are spending a lot of time talking about things, figuring things out. If the instruction is structured the right way, they actually cover more actual topics, and the students learn them much better. And the students it's been interesting to see the student response there, because we've gotten, for a large number of these classes, we've had nearly all the students submit anonymous, you know, so we don't know who they are, but their views on the teaching methods that are being used. And basically 90% of the students, or 90% of the comments are positive. Almost all of them are extremely positive that, Stanford students, it's a very selective group, but they're finding this to be much more effective way to learn physics, and they really are advocating now for all their classes to be taught that way. And it's been interesting to see that the faculty, although they didn't know how to teach this way when I got there, but now that they've learned to teach physics this way, and they find that they're interacting much more deeply with the students, and in fact, the students are more engaged, are much more expert in thinking about the subject, and that's kind of more fun for the faculty to teach when the students are that way as well. So the instructors are also finding it actually a much more enjoyable way to teach this material. So with that, I'm going to just end with some references that you. If you want to learn more about this subject and more about learning, these are some good things to read, particularly from a student's perspective. This book, The ABCs of How We Learn, this is really taking a lot of the basic research on learning. Dan Schwartz is one of the experts in this, and taking a lot of technical studies and writing them in a way that is pretty easy for people to understand them and think about how they can use this in their own learning, and then other things you can read here if you want. And I'll remind you that these slides will be all available, so you can go and look up all these references. And so with that, I've left a reasonable amount of time now for comments or questions from the audience. Just remember, you'll have to raise your hand and keep it up, and then the people with microphones can come around and get it to you so that it gets recorded. Thank you.